In this video, we'll take a closer look at stationary points and how the second derivative can help us decide whether they are maximums, minimums, or points of inflection. There are three types of stationary points: maximum points, minimum points, and points of inflection. On the graph, you can clearly see there is a maximum point there, there is a point of inflection there, and there is a minimum point there. Let's take a closer look at maximum points. Consider what happens to the gradient at a maximum point. It is positive just before the maximum point, 0 at the maximum point, then negative just after the maximum point. The value of dy over dx is decreasing, so the rate of change of dy over dx with respect to x is negative. That means that the second derivative is negative. So if the second derivative is negative, we get a maximum. Now let's take a closer look at minimum points. Just before the minimum point, the gradient is negative. At the minimum, the gradient is 0, and just after the minimum point, it is positive. The value of dy over dx is increasing, so the rate of change of dy over dx with respect to x is positive, i.e. the second derivative is positive. Now let's look at points of inflection. At some points, the derivative dy over dx is 0, and the second derivative is also 0. Two such points are shown in the sketches. They are called points of inflection. In the first point of inflection, we've got a negative gradient, 0 gradient, and negative gradient. In the second one, we have a negative gradient, a 0 gradient, and a negative gradient. Note that at a point of inflection, the gradient does not change from negative to positive. It either goes positive, 0, positive, or negative, 0, negative. Also note that the second derivative is also 0 at some maximum and minimum points. To find this type of stationary point, consider the gradient at each side of it. If you need to sketch a graph, you need to do the following. Find the stationary points. So find an expression for dy over dx and put it equal to 0. Then solve the resulting equation to find the x-coordinates of the stationary points. To find out what type of stationary point is, find the second derivative and substitute each value of x to find the kind of stationary point. Positive suggests a minimum, negative a maximum, and 0 could either be a point of inflection or either a maximum or minimum. Then find the point where the curve meets the axes. Substitute x equals 0 in the curve's equation to find the y-coordinate of the point where the curve meets the y-axis. Substitute y equals 0 in the curve's equation. If possible, solve the equation to find the x-coordinates of the points where the curve meets the x-axis. Sketch the curve, Then use a graphical calculator to check. Example. To sketch the graph y equals 4 minus x squared, find the derivative, which is 4 minus 2x. Put the derivative equal to 0. This gives 2x equals 4, so x equals 0. Find the second derivative, which is equal to minus 2. This suggests a maximum. If we substitute x equals 2 into the equation for the graph, we get y equals 8 minus 4, which is 4. So now we have the coordinates 2, 4, and we know it is a maximum point. Then we need to know where it crosses the two axes. So we put in x equals 0, and we get y is equal to 0. We put when y equals 0, we get 4x minus x squared is equal to 0. Factorize, giving x brackets 4 minus x. So x is equal to 0 or 4. So the curve crosses the axes at 0, 0 and 4, 0. We now have all the information needed to draw our graph. For the second example, we want to sketch y equals 2 plus 3x squared minus x cubed. Find the derivative, dy over dx, giving us 6x minus 3x squared. To find the stationary points, put the derivative equal to 0. This means we have 6x minus 3x squared equals 0. Factorizing gives 3x brackets 2 minus x equals 0. This gives us the solutions x equals 0 or x equals 2. Now find the second derivative, which gives us 6 minus 6x. Substitute in x equals 0 and x equals 2 into our second derivative, which gives us a positive value when x equals 0 and a negative value when x is 2. So substituting the values of x into our original function, y equals 2 plus 3x squared minus x cubed. When x is 0, we get y equals 2. And when x is 2, we get y equals 6. That means 0, 2 is a minimum point and 2, 6 is a maximum point. We now need to find where it crosses the two axes. So when x is 0, we get y is 2. When y is 0, we get 2 plus 3x squared minus x cubed is 0. Solving such a cubic equation is difficult and not necessary, as it is possible to sketch the curve using just the stationary points and the fact that it crosses the y-axis at 0, 2. The final example is to sketch the graph y equals x to the power of 4 minus 4. So find the first derivative, which is 4x cubed. Find the stationary points by putting the derivative equal to 0. This gives 4x cubed is 0, so x is 0. Finding the y value at x is 0 gives us y equals 4. We then find the second derivative, which is 12x squared. This gives us a value of 0 when x is 0. In this case, the stationary point could be a maximum, a minimum, or a point of inflection. To find out which, consider the gradient before and after x equals 0. When x is negative, the derivative, which is equal to 4x cubed, is also negative. When x is positive, dy over dx is also positive. So, at the point 0 minus 4, there is a minimum point. Now we need to find the points where it crosses both axes. So when x is 0, y is minus 4. When y is 0, x to the power of 4 minus 4 is equal to 0. That means x to the power of 4 is equal to 4. So x squared is equal to 2, giving x is equal to plus or minus the square root of 2. So the curve crosses the axis at 0 minus 4 and crosses the x-axis at minus root 2, 0 and root 2, 0. We now have all the information we required to draw the graph of y equals x to the power of 4 minus 4.